Good day. The purpose of this presentation, although ostensibly to discuss the asymptotic normality of the total claims of an insurance company, is really to introduce the viewer to the idea that there is more than one central limit theorem. And in particular, we will be discussing what is known as the Lindeberg central limit theorem. We will then show that this theorem has an application to the distribution of the total claims of an insurance company, although the applications of that are much greater. So the game plan to do this will be to take us through the introduction. We'll discuss some of the history behind the central limit theorem. We'll look at some examples, and then we'll show what the Lindeberg version of it looks like in practice and what its implications are. So here we go. The first thing to keep in mind when we're discussing these things is that actuaries have a reason to consider distributions other than normal. In particular, when we're speaking about claims, we often use what we refer to as distributions with heavy tails. And so in a previous presentation, we discussed the work of, say, Charles Hewitt, and he applied the gamma distribution to claim loss, claim severity. You might also consider Pareto distributions, log normal distributions, Weibull distributions, anything that has a heavy tail. And the reason that you care about such things is because we know that insurance claims, well, sometimes things get a little out of hand. Sometimes juries come back with wild verdicts. In current parlance, we refer to them as nuclear verdicts. And so even if there is something somewhat normal looking about the severity distribution, way out on the tail, there are occurrences that can still take place. You can still have very, very, very large claim settlements. And so that's why actuaries are interested in distributions other than normal. And so we recall what we learned when we went through Statistics 101 is that we basically had two theorems that were, like, say, the centerpiece of the class. One was the strong law of large numbers, which basically said that the statistic, the sample mean, converges, probabilists would say almost everywhere, or rather almost surely. Measure theorists would say almost everywhere. Converges almost surely to the actual mean of the distribution. And so that tells you where it's going, but it's still, for any given n, the sample mean is still a random variable. And so you can ask, well, what's its distribution? And the answer was, well, it's asymptotically normal. And that's the content of the central limit theorem. The problem with both of these results from a practical perspective is that they both rely on what are sometimes referred to in an abbreviated form as IID assumptions. That is to say, the random variables are independent and they're identically distributed. And so those are two relatively strong assumptions. And of course, in practice, certainly although you might make an argument for, oh, well, our claims are independent of one another because this claim, has, if it's auto, say this claim had Bob in Georgia backing into a mailbox, and this other claim had Sheila in Alaska, um, you know, T-boning Tesla or something like that, right? What do they have to do with each other? They're independent. Okay, I'm willing to buy that. But given the examples that I just gave you, you can't really make a case for identically distributed. Are we really going to sit here and say that, oh, yes, backing into a mailbox, yes, the distribution of severity coming out of that is just the same as the distribution of severity T-boning a Tesla? Probably not. So we, in fact, would not make an argument for the identically distributed assumption in these theorems. And so then you say to yourself, well, then what good are they? Like, what can we do with this information? I'm glad I took the class, but what can I do with this information? And so the answer to this is, well, you have to start by realizing that, there's actually more than one central limit theorem. And so this particular this particular um, theorem is essentially named by George Polya in 1920. He says he's writing in German, really. He's writing in the Mathematische Zeitschrift, and he writes, generally known that the appearance of the Gaussian probability density can be explained by one and the same limit theorem, which plays a central role in probability theory. So that's from whence the name comes, okay? But as far as we can tell, it goes back to the 1700s with Abraham de Moivre, and he basically, if you read the work in which he does this, he's basically trying to approximate probabilities associated to a binomial distribution, and he winds up using something very similar in kind to a normal distribution. And the reason why he's doing this is because, again, this is 1733. He does not, in fact, have all the computational resources at his disposal that we have today. And if you've ever tried to do calculation with the binomial distribution for even a modest number of trials, just the numbers get out of control real quick. The calculations get out of control real quick. So he needed something to approximate those results. And so then after that, Laplace comes along in 1812, and he uses the normal distribution to approximate even more complicated distributions. And in fact, there is not only a single book written on the history of the central limit theorem. The one I used for this video was the one by Fisher, his book, A History of the Central Limit Theorem from Classical to Modern Probability. But even in that book, Fisher has a paragraph where he lists other books about the central limit theorem. So there's quite a lot of material written on the history of the theorem. And so the men that I'm mentioning here, it's just a couple guys. There's like way more of them if you go and read these books. And in fact, I recommend the one by Fisher. He's actually got notes from, who was it? Dirichlet, I believe, the actual German notes reprinted in one of the chapters in his text. Interesting point about Laplace here. If you ever actually look at the proof of the central limit theorem and its grand generality, one of the things you note is they make use of what are known as characteristic functions. And you say to yourself, gee whiz, that looks an awful lot like a Laplace transform. Well, that's the reason why, is because Laplace was one of the people who worked on this problem, and he introduced the idea of using characteristic functions. Like I said, the fellow that with whom we're going to concern ourselves today is Lindeberg. He wrote the version of the theorem that we'll be discussing today. That came in 1922. And as far as I can tell, the most general formulation of the central limit theorem that you can find comes to us from Moyer in 1953. And she was looking at, so instead of your random variable just taking numbers as its values, it took as its values elements of a Hilbert space. So a great deal of work has been done to generalize the results of the central limit theorem. There are, in fact, many central limit theorems. Before proceeding from the historical perspective, I want to draw your attention to a paper by Lacam, who wrote also on the history of the central limit theorem, and opened his paper with the following. In the beginning, there was de Moivre, Laplace, and many Bernoullis, and they begat limit theorems. And the wise men saw that it was good, and they called it by the name of Gauss. Then there were new generations, and they said that it had experimental vigor, but lacked in rigor. Then came Chebyshev, Lyapunov, and Markov, and they begat a proof. And Polya saw that it was momentous, and he said its name shall be called the Central Limit Theorem. Then came Lindeberg, and he said it was elementary, for Taylor had expanded that which needed expansion, and said it twice. But Levi said that the Fourier transforms are characteristic functions, and he said, Let them multiply and bring forth limit theorems and stable laws. And it was good, stable, and sufficient. But they asked, is it necessary? Levy answered, I shall say verily unto you, that it is not necessary, but the time shall come when Gauss will have no parts, except that they be in the image of Gauss himself, and then it will be necessary. It was a prophecy. And then Kramer announced that the time had come, and there was much rejoicing. And Levy said that it must be recorded in the Bibles, and he did record it. And it came to pass that there were many limit theorems, and many were central, and they overflowed the chronicles. And this was the history of the Central Limit Theorem. Okay, so before proceeding to Lindeberg and its application in actuarial science, I want to go through a few examples here and illustrate what the central limit theorem, the typical one that you find, what it even means. Because I don't think that, at least when I was in school, that this was demonstrated in any sort of way. And so we'll look at it for the gamma, Weibull, and log normal distributions. And so keep in mind, again, that when these guys are formulating the central limit theorem, they are doing theoretical math, but they don't have the computational capacity that we do. And so everything that they're doing theoretically, but they are unable to generate any set of large number of examples to help themselves with this, to try to improve their intuition. But we do. So let's use it. So for each one of these distributions, I'm going to assume they have approximately mean 12,500 and a variance of approximately 1/2 of 150,000 squared. Now, why approximately? Well, you'll find out later. Why these numbers? Well, because I was trying to think in terms of the severity of certain lines of business and also the standard deviation that goes along with it. And um, the standard deviation when you're talking about claim severity is often multiples of the mean, and so that's what's going on here. But here's the thing: is like, well, what is the central limit theorem telling us? Well, it's saying, look, draw a sample of some size, say 10,000, and compute the mean. The distribution of the mean is normally distributed. What does that mean? Well, what it means is that if you did that process a bunch of times, drawing a sample of size 10,000, computing the sample mean, drawing a sample of size 10,000, computing the mean, drawing a sample of size 10,000, computing the mean. When you take all of those means, those sample means, when you take all of the sample means, not the original distribution, the sample means, what happens is that they will look normally distributed. If you make a histogram, it'll look normally distributed. If you look at the uh, empirical cumulative distribution function, which comes from that, it should look very similar to a one coming from a normal distribution. And so what we're going to do is, because we have the computational capacity, we're going to do just that. We're going to draw a sample of size 10,000, and we're going to compute a mean, and then we're going to do that 1,000,000 times. And then we're going to see what happens. So, without further ado, the original distribution, and that's the beauty of the central limit theorem, right? It's almost a something for nothing theorem. No matter what your starting distribution is, your sample mean is asymptotically normally distributed. So we started with a gamma distribution that had this mean and this variance, all right? And then we drew from that 10,000 times. We calculated the sample mean. We drew from it 10,000 times. We calculated the sample mean. We did that 1,000,000 times. And what happened when we did that 1,000,000 times? Well, we got something with a mean that's very similar, which is what it should be, and a variance that's roughly 10,000 times less than the variance of the original distribution, which is also good. So when we plot then the the PDF, what are we expecting? So this is a normal curve here. This is a normal density function. And in our case, because the sum of gammas is gamma again, and then a gamma divided by a constant is again gamma, we actually, ahead of time, we could calculate the theoretical distribution of the sample mean, and that's the orange here. That's what that looks like. Um, but then the other thing is that because we did this a million times, we've got an empirical CDF. From that, we can calculate, and I know this is going to sound odd at first, you can calculate an empirical PDF. How do you do that? Well, the answer is, well, by definition, the density function is the derivative of your cumulative distribution function. And you might say, but we don't have a formula for a cumulative distribution function. It's like, who cares? Just take the values of your cumulative distribution function, figure out where they took place, and then just use use a numerical approximation for the derivative and plot that. But isn't that going to be ugly? Yes, it is. It looks like this. Yes, it's going to be ugly, but it still gets the point across, right? That even the empirically estimated density function, it kind of just lays right across. Yeah, there's a lot of noise, but it lays right across roughly where it should be. So even though we started with this gamma distribution, when we sample from it 10,000 times, compute the sample mean, and then do that a million times and plot it, this is the kind of thing that you get. And then if you look at the histogram of it, well, lo and behold, yeah, that looks pretty darn normal too. And so this visually is what the central limit theorem is telling us. De Moivre didn't have this technology at his fingertips, but we do. And so we can use it to illustrate what's going on. Okay, so moving on, let's take a look at a viable distribution. So this was the mean of the original distribution. This is the variance. Sample from it 10,000 times, compute the mean, do that a million times. What do you get? Well, you get something which has a mean of roughly what you would expect, and a variance again, 10,000 times less than the variance of the original distribution. How does it look? Well, there's the PDF that we're expecting. That's our density that we're expecting. That's a normal density. Now, in this case, the sum of variables is, I don't know. So it was hard to calculate exactly what the distribution of your sample mean is going to be. But nonetheless, you could see that the empirical one pretty much, lines up with the purple one. It doesn't go right through the middle, but a little bit of tail action out here. And when you look at the histogram again, you get something that looks pretty normal. This one, the mound, if you will, is over here. A little bit more tail on the viable, heavier tails. So out here is where you get your nuclear verdicts, that sort of thing. Okay, moving on to a log normal distribution. All right, so here was our mean, here's our variance. That's from the log normal distribution. Sample from it 10,000 times, compute the sample mean, do that a million times. What do you get? Well, you get a distribution whose mean is roughly this, and your variance is this, which is 10,000 times less than that. So everything's looking the way it should. So let's take a look at, all right, so this is the density we're expecting here. This is a normal density, and what do we get? It was, okay. Well, again, the PDF, or rather the empirical PDF of the sample mean, it certainly has a normal look to it, but it's not really quite aligning as tightly with the modeled PDF, with the actual normal PDF. And when you look at the histogram, it's all piled up over here with like a much longer tail than we saw even on the Bible. And so a reasonable question at this point would be something like, hey, dude, I was with you at the gamma, pretty much with you at the Bible. This one just doesn't seem to be lining up as well. So, well, what's going on? Well, here's the thing, is that let's take a look at the PDFs, the density functions here, and let's just see what's going on. So this is the Bible, and you can see that the density of the Bible is pretty much start here, and it goes down very quickly. I didn't even graph the gamma one because the gamma one is pretty much nearly all of the probabilities is concentrated near zero and then just like shoots down. And so if Excel was calculating it and the PDF takes values somewhere around 10 to the 132nd power, something like that. Quite large. Almost looks like a Dirac delta kind of thing. All right. What about the log normal? Well, it looks like this. So you see this is what's giving you the fatter tails, the heavier tails. And that's kind of what's driving this. And so when you say, geez, it just doesn't seem like it's adhering as much to the normality as we would like, it's like, yeah, well, graphically, we're getting a sense about why we're seeing heavier tails here. Here's something else. You can do some calculations, right? Which is that we can make calculations that give us a sense of how heavy tails are. So gamma has a skewness, so that's the calculation, the skewness, it's the third centralized moment of 17 roughly. What about the Weibull? It had heavier tails. Lo and behold, it has a skewness of 62. And the log normal's tail is has a skewness of 640, roughly something like that. And you can actually figure out the exact point at which the heaviness takes over on the log normal tail. It's heavier than gamma past 3 million, and it's heavier than Weibull past 7.7 million. And so that's what's going on here, is that the reason that the sample mean was not adhering as nicely to the normal distribution for the sample mean is that, well, it's got a heavier tail. And so then you might say, well, that's great, but I thought we wanted to assume normality here. Don't we have any sense of goodness of approximation? And the answer is yes, we do. In fact, there's something called the Berry-Esseen theorem. Okay, and so this comes to us courtesy of Carl Gustav Esseen and Andrew C. Berry in 1942 and 1941, respectively. So there is a sense of it. And what is that? Well, it provides a bound on the convergence of the distribution using the absolute value of the third central moment, which we just discussed in the skewness. And so basically, it's if this is the distribution of your sample mean, and this is just your standard normal distribution, uh, then you can actually calculate. You can get an upper bound on how close those guys are to each other. And what is that upper bound? Well, this piece of it right here, the expected value of the original distribution minus its mean, this thing over 3. This is very similar to the skewness calculation. Uh, but now we have the square root of n here and this 0.8. 0.8, 0.8, 0.8. Where does 0.8 come from? Well, again, it turns out that the number here, mathematicians have been whittling away at it for years. And so originally this number was larger. This 0.8 to us comes from Van Beek in 1972. And for instance, Peter Hall has made the early part of his career calculating the accuracy of the normal distribution in all sorts of different cases. So much so that he wrote a book in 1982 called Rates of Convergence in the Central Limit Theorem. So again, the richness underlying the Central Limit Theorem is quite grand. So what this is saying is that, hey, look, um, if it's not sufficiently normal for you, maybe you need to up your sample number. So okay, fine, let's do that. So we're going to sample from the exact same distribution that we did last time, except now instead of taking a sample size 10,000, we're going to take a sample size of 1 million. And so once we do that, now things look great. And the log normal count, or the histogram of it, looks much more normal for us. Okay, so before proceeding to Lindeberg and talking about the asymptotic normality of the total claims of an insurance company, I wanted to illustrate what the central limit theorem in its basic form is telling us even in the first place. And basically what it's saying is, if you want to visualize it, you have to calculate many sample means. But we can do that. So we did it. Okay, on to Lindeberg. So what's Lindeberg telling us? So I'll speak through this equation here in a second, but basically the question becomes, hey, we've got the central limit theorem. It relies on these two assumptions, IID, independent and identically distributed. Can we relax some of those distributions so that we might widen the application of the theorem? And the answer is yes. And Lindeberg said so in 1922. And so, okay, well, how do we do that? And Lindeberg said, we're gonna get rid of, we still want to maintain independence, but we're gonna get rid of the idea that things are identically distributed. So now we're just gonna have all sorts of random variables that we're adding up. Okay. So uh, what do we do? To understand what Lindeberg was saying. And so we're starting with this here. So if you look on the left-hand side, this is the thing that's asymptotically normally distributed with uh, standard normal distribution here. Okay. So this is the thing you typically see in your Stats 101 class. And what we're going to do is we are going to rewrite this so as to motivate what Lindeberg was up to. And so when you do that, what we're going to do is, this is your X bar. So we're going to, this is X bar is the sum of your X's divided by N. So we're going to take out the N. And so when we take out the 1 over N, that's why we have an N here next to mu. And that 1 over N will cancel with like part of, well, I'll cancel the whole square root of N thing here, and will leave us with a square root of N in the denominator. So that's that. Now, in the denominator, what are we going to do? Well, we're going to take our standard deviation and we're going to write it in a somewhat strange fashion. We're going to take the square root of it squared, and then we're also going to multiply and divide by the square root of n. Of course, the reason we're doing that is to cancel with the one that came down. Okay. And so these things cancel here. Now, this sigma squared here, n sigma squared, how do we think about that? Well, again, in the original theorem, we assumed identical distribution, which means that we could rewrite n sigma squared as just the sum of all the sigmas from all the different variables. These are all the same in the classical case. Similarly, up here, we're going to write n mu as the sum of all the mu's, which again, in the classical case, each one of these mu k's is the same thing. But now what we've done is we've taken the classical formula, right, and we've written it in terms of its individual parts. And the reason we've done that is because we want to now assume that these things are not, in fact, the same, and then see what happens. So the classical theorem says this thing is asymptotically standard normal distributed. We'd like to make a similar claim about this thing in the case when these mu k's are different and these sigmas are different. Okay, well, if we get rid of the identical distribution assumption, but we can't just get rid of it. Like, we got to replace it with something. Well, what do we replace it? And the answer is, well, let's look at the partial sums here of our variances. We'll call that Sn squared here. And what else do we need? Well, we need this thing, obviously. So what is this? Okay, reasonable question. So this thing is just awful. So let's take a look and see if we can make some sense of this thing, right? So if you forget about this piece here, this indicator function, this indicator function is saying, look, for all we need this thing to be true for all epsilon greater than 0, and this indicator function is indicating when the difference between the variable and its mean exceeds epsilon multiplied by Sn, the sum of the variances. So let's forget about this guy for just a second and see what this thing is saying. So if we forget about this guy, what do we have? The expected value of x minus mu squared. What is that? Well, that's just the variance of the kth variable. And so forgetting about this factor here, what is, if you do that, then you're just summing the variances here. And that's exactly what Sn squared is. It's the sum of the variances. So this whole expression here is always at most 1, because if this indicator function is always turned on, then you just get Sn squared. That's that. Okay. So what next? Well, if this thing is going to go to 0, what has to take place? Well, among other things, this sum here better go to infinity, because if this sum is bounded, then ain't no way this thing is going to go to 0. So we need the sum of our variances to actually be unbounded. And finally, what else? So like I said, this thing is always bounded above. Whoops. Always bounded above by, there we go. Always bounded above by 1. And so now what's this thing going on in here? Well, what this is saying, this is, like I said, this is the indicator where the variable is kind of far away from its central value, its mean, right here. And so what this is saying is that asymptotically, this doesn't happen too often, is really what that's saying here. And if that's true, if this doesn't happen too often, because if x doesn't wander too far away from its mean, this piece here will be 0. And then when you have a bunch of zeros in the tail and you've got something going to infinity here, then you're going to go to 0 there. And so that's what Lindeberg does. So there's no free lunch, right? If you're going to get rid of the assumption of identical distributions, well, you got to replace it with something. Lindeberg replaces it with this. Okay. Now, for our purposes, you might say, okay, this is kind of a technical criterion, Ian. How does this map onto application? And the answer is, well, here's the thing, is that if your x's are uniformly bounded, that is to say, if your variables are uniformly bounded, then it's trivial to show. I mean, it's a math proof, but it's trivial to show that this holds. And so if that's true, then you're in good shape. Now you might say, well, geez, that's a heck of a assumption. And yes, mathematicians would be bothered by it, but we actuaries don't need to be bothered by it. And the reason we don't need to be bothered by it is because what's it saying? If we're talking about a claim severity, all it's saying is that there is a maximum value that any given claim can take. And we already know that, because the maximum value that any claim can take is all of the money in the world. So uniform boundedness for application purposes is no problem whatsoever. Okay. And similarly, our variances, we do expect that to go to infinity. And so what that means then is that for all intents and purposes, we don't need to assume that our claims are identically distributed. The fact that we know that they're independent, or we presume that they're independent of one another, is sufficient, because we know that the sum of the variances go to infinity, and we know that they're uniformly bounded. So we're in good shape. And so now you can just do the typical kind of argument, right? So here's the sum of your claims right here. And you say to yourself, well, what's the probability that that's less than or equal to some value? Call it S. You go, I don't know. Well, Just do the usual thing, right? Subtract off your means, divide by, in the classical sense, we would say the uh, standard deviation, but in this case, we're going to divide by the square root of the sum of the variances. That's the equivalent in this case here. Okay, that's equal to this guy here. But Lindeberg now tells us, well, hey man, you've satisfied the criterion of Lindeberg's theorem. So this probability can be approximated by the standard normal right here. And so what is this guy? Well, this is just a normal random variable with mean, the sum of the means of the claims, and variance, the sum of the variances of the claims. So we're in good shape. And so for estimation and verification purposes, we could just assume that while the individual claims can be quite skewed, can have heavy tails in their distribution, the individual claims might have all sorts of distributions. Who's to say? But there's some. The sum of them, according to Lindeberg, is going to be asymptotically normal. Okay, well, you might say, that's all well and good, Poindexter, but what does this look like in practice? Reasonable question. And so now what we're going to do is, just like in the first part of this discussion here, we showed examples of what the central limit theorem looks like in practice, the classical central limit theorem. We are going to show what the Lindeberg version of it looks like in practice. So here's how we're going to do it. We are going to try to violate the identical distribution assumption as vigorously as possible. And so to do that, what we're going to do is we are going to randomly select from 12 different families of distributions. Now, where did that come from? Well, base R, the programming language I use, comes equipped with 17 different distributions in it. So you might say, well, why not just use 17? And the answer is that, well, because the Cauchy distribution has no mean, the hypergeometric distribution has 3 parameters, so it's not specified by its mean and its variance. The multinomial distribution is vector valued, so that's out. And then F and students T, I found them to be somewhat numerically unstable in testing, so I threw them out. So that leaves us with 12 different distributions. So we're going to violate the identical distribution assumption. So we're going to randomly select from one of 12 families. Okay. And then we're not going to be content with having a fixed mean and variance for each one of those families. Oh, no, 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 no. No, we're going to, once we've randomly selected our family, we're going to randomly select the mean for the distribution, subject to distributional constraints. So for instance, a beta random variable takes values between 0 and 1. So, we don't go with the 25,000 for beta. And we're also going to randomly select the variance for the distribution that we're going to be using. And once we've randomly selected the mean and variance, we'll perform our method of moments to get the parameters for the distribution. And then finally, we'll select from the distribution. So for one shot of this, we're actually making 4 different selections. We're going to randomly select the family. We're going to randomly select the mean. We're going to randomly select the variance. And then once we have the family, the variance, and the mean, then we're going to randomly select from the distribution. And that 4th one is going to be our actual observation. So these observations could not be more different from one another. So we're going to do that 10,000 times. So and we're going to add it up. So that's going to be the total, right? So basically the thinking that we have here is that we have 10,000 different claims. We're not making any sort of assumptions. I guess we're saying it's one of 12 distributions, but we're trying to make as few assumptions as possible about the distributions of these 10,000 claims. And we're just going to select from here and over there and here, and they couldn't be more different. So we're going to select, we're going to do that 10,000 times. So, roughly we're going to make in total 4,000 different random selections, or 40,000. And then we're going to add it up. And then we're going to do that a million times, just like we did with the gamma, viable, and log normal. And then we're just going to see what happens. Now, you might be saying to yourself, gee whiz, how do you even get a handle on such a thing? And the answer is, well, we just have to remember our laws of conditioning, right? So the expected value of x is the expected value of the conditional expectation. The variance of x by the law of total variance is the expected value of the conditional variance plus the variance of the conditional expectation. And so how does this look like in practice? Well, suppose that the family in question that we selected is normal. If it's normal, then our mean, which we randomly select, well, what's that going to be? Well, that's uniform on 0 to 25,000. That is mean 12,500. And the variance, what's the variance going to be? Well, it's going to be the expected value of the conditional variance. Well, the conditional variance was on uniform on 0 to 150,000 squared. And so that's what gives rise to 1/2 of 150,000 squared, plus the variance of the mean. Well, what's the variance of the mean? Well, it's the variance of a uniform random variable from 0 to 25,000, which is 25,000 squared divided by 12. And so we can, in fact, calculate, if we know the family, we can calculate what the mean and variance, their expected values are going to be. And similarly, if we do a Poisson random variable, you can do the exact same thing, except the difference in this case is that you say to yourself, oh, wait a minute, with a Poisson random variable, the mean and the variance are equal to one another. So once you've selected the mean, you're done. The mean, it was selected from 0 to 25,000, so therefore the expected value of that is just 1/2, 25,000. And so what you can do is you can do this exercise for each of the 12 families, and then you apply the same conditioning again, except now that you'll be conditioning on the family that you've selected, and all families are selected with equal probability. And so when you do all that, what do you get? Well, you get a random variable with mean roughly $11,500, $11,458, and this variance here, okay? And so when you sum all of that together, you should get something whose mean is roughly 10,000 times that, which is what you have right here, and whose variance is 10,000 times that, which is roughly what you have here. So we violated the identical distribution assumption as much as possible. What are the results? Well, if Lindeberg is right, the density should look something like this. What does it look like? The empirical density looks like that. So even though we were as not identically distributed as possible, in the end, the result is that the sum is still pretty darn normal looking. Here is your histogram there. So what's the point of all this? Well, when we're talking about an application for the insurance industry, what it means is that if you are doing, for instance, say simulations of a total set of claims, you should expect those totals to be approximately normally distributed. And that's what Lindeberg tells us. What's the use of that? Well, what it means then is that it gives you a way to check if the results of your simulation even make sense. So it's a sanity check on the results of your simulation. It allows you to do a back of the envelope calculation when you're trying to get a sense of how big your total set of claims are, what the low end and high end of that is going to be. And finally, it allows you to sort of, if you will, slough over technical details when you are communicating these results to stakeholders who might not be technical. And the reason for that is that most people understand the bell curve. Most people understand things that look like that. Most people have seen that at one point in time in their life. And what this allows you to do is it allows you to go into those meetings and draw those graphs and know that while, yeah, it might not be absolutely 100% normally distributed, it's approximately so. And so therefore you can draw those graphs with impunity. You can calculate, say, if you have a high end of 70% and a low end of 30%, something like that. You can look at the centiles from the empirical runs that you perform, the simulations that you perform. You could figure out what normal curve is going to have that, and then you could draw that curve. And you can say with honesty that what you're showing them is really indicative of what is taking place in the simulations for the total value of a set of claims. I hope you have found this presentation to be useful. If you have any questions, please leave them in the comments.